In this video, we'll introduce geometric sequences. We'll start with an area example. Let's call this figure the first term in our sequence. It has an area of 1. Now, what I'd like to do is double the area of this figure. So our second term in the sequence has an area of 2. Now I'm going to double this area to get 4. I'll double this area to get 8, and we'll keep repeating this process. When I double this area, I get 16. What will be the area of the next figure? It will be 32. Doubling that, we get an area of 64. And we have room for one more figure here on our screen, and we get 128 as the 8th term in this sequence. This sequence of numbers can be thought of as a geometric sequence. It's a sequence of numbers where each term after the first is found by multiplying the previous one by a fixed non-zero number called the common ratio. So we're going to be looking for multiplicative relationships to identify geometric sequences. Here I'm multiplying 2 times 3 to get 6, 6 times 3 to get 18, 18 times 3 to get 54, so 3 is my common ratio. This sequence of numbers is a geometric sequence. We have notation and vocabulary that's associated with geometric sequences. Each term has a subscript attached to it. And so A sub 1 is the first term in the sequence. A sub 4 is the 4th term in the sequence. We call these numbers terms. So 2 is the first term in the sequence. 3 is known as the common ratio of this geometric sequence. The next term in this sequence would be found by multiplying 54 by 3, that's 162. The 7th term in the sequence, A sub 7, we could do this manually by listing out the first 4 numbers in the sequence that are given, multiplying each term by 3 to get the next term. The 7th term in the sequence is 1,458. We can see that with geometric sequences, these numbers get very large very quickly if the common ratio is bigger than 1. Now how about a formula for the nth term? That will come in handy. Let's try to derive the formula by noticing that all of the numbers in the sequence are based on the number 2, which is the first term in this sequence. So 6 would be 2 times 3. 18 can be thought of as 2 times 3 times 3. 54 is 2 times 3 times 3 times 3, etc. And when we look closely, we know that in our formula the number 2 will be there, but 3 to a certain power will be there. And the power will be 1 less than the term number. So let's kind of make sense of this. The first term, as we know, is called A1. Let's call the common ratio R, just to give it a variable name. The nth term we'll call A sub n. And here's our formula. A sub n equals A sub 1 times R raised to the power of n minus 1. In the previous slide, we found the 7th term manually by extending the sequence. This time, let's find the 7th term by using the formula. We'll put 7 in place of n. We'll type 2 in place of the A1, and our R, our ratio, is 3. And now we'll just manipulate these numbers. We'll do 7 minus 1 to get an exponent of 6. 3 to the 6th power is 729, times 2 will be 1,458. The 7th term in this sequence is 1,458. Here, let's do a practice problem with some different numbers. Notice these numbers are increasing in value as we work from left to right. Therefore, I'm multiplying by a number bigger than 1. My common ratio is going to be bigger than 1. we want to find a formula for the nth term of this sequence. So remember the general form, a sub n equals a sub 1 times r to the n minus 1 power. In this case, a sub 1 is 5, and my r, my common ratio, is 2. So to find the 7th term in this sequence, a sub 7, it's going to be 5 times 2 to the 7 minus 1. That's 5 times 2 to the 6th. That'll be 5 times 64, which is 320. The 7th term in this sequence is 320. So we'll do one more example, but this time as we read from left to right, the numbers are getting smaller. Often we like to think about that as dividing by a number, but with the case of geometric sequences, it's important to note we are still multiplying by a number. We are just multiplying by a number less than 1. So to find a formula for the nth term of this sequence using the general formula, we're going to recognize that our a sub 1 is 640. And the number I'm multiplying each term by is a half. So here's my formula that I'll be using. So if I wanted to find, say, the 9th term of this sequence, I would substitute 9 for n. I would now rename this as 640 times a half raised to the 8th power. And that is 640 times 1 over 256. If I were to divide 640 by 256, I get 5 halves, or 2 1/2. So the 9th term in this sequence is 5 halves. That's our introduction to geometric sequences.